Okay, this is lecture 22, and we're to the point where we're running out of things to say, so we're going to catch up on some definitions, which basically is CISC versus RISC and Harvard versus von Neumann. And then we're going to do our first new type of example, and I like these examples for reasons I'll say later. This is really the last, this example is really the last new thing we'll do in the course. So there's a couple standard computer architectures out there, and it's, you know, these are really old terms, but people still use these terms. And if you claim you took a course in computer architecture, people are going to ask you to explain the difference between these two architectures. So up here we have a basic computer architecture, has the three parts as we know and love it, essentially CPU, I/O, and memory. So generally speaking, this memory here, we always draw it as one, but that's just to make it simple. Now, there aren't necessarily just one memory in every computer, and that's how these two architectures differ. So these two architectures, if I remember correctly, Princeton and Harvard had a computer design contest. I believe this is the 1940s. And these architectures were what they came up with. So this is also known as a Princeton architecture. I can see my pen is wanky. And so Princeton versus Harvard, what most people call it von Neumann, so we'll go with von Neumann. So with a computer memory, we're storing two things. We're storing data and we're storing instructions. So just kind of generic data, and then we're storing instructions, which is essentially program memory. So the difference between these two architectures, in the more simple version, we'll get into both versions, the version that everyone accepts it as, is that okay, so I got the pen fixed. And so essentially the von Neumann architecture, it has one memory which is shared between data and program memory. Now this is kind of sort of what we're using with the RISC-V. We only have one memory unit. Okay, so this of course doesn't include the register file. Okay, so the other architecture is Harvard architecture, and what the difference being that essentially it has two memories, and one memory is dedicated to the data memory, and another memory is dedicated to instructions. So essentially the difference between these is Harvard has two memories, and one for data and one instructions. Von Neumann has one memory, and it's shared by data and instructions. So roughly speaking, the RISC-V, since we have one memory, it's going to be a von Neumann architecture. Okay, so more on that later. It's a little bit confusing. So once again, if there was one great way to do it, everyone would be doing it that way. But what you see out there is lots of Harvard and von Neumann architectures. So the obvious differences are, I'm going to go over this Harvard architecture, and it does seem like the Harvard architecture does have some great advantages. Okay, so first advantage here is the fact that you don't see this in RISC-V, but in many architectures, the width of, we'll say, of the data of the register file is different than the width of memory. Okay, so that was really handy for us. So when we were pushing and popping values, it was 32 bits. Register went into kind of a 32-bit memory, etc., etc. I know it was byte oriented, but it still fit anyway. So the issue is if you had like the old processor we had, it had an 8-bit memory for just general data storage, but it had a separate memory for program memory, which is 18 bits. Now there's a mismatch there, and so if I was going to store 8 bits into 18 bits, it would be not as efficient, and it would be really even if I did do it, it would be really clunky to get the data in and out. Okay, so once again, we're lucky. The memory was configured such that it's easy to get data in and out of it, even though it was byte oriented. And once again, what we're trying to do is get 32-bit or 4-byte values in and out of memory. So once again, summarize that. If the instruction words were of a different funny bit length than the registers, it would certainly support a Harvard architecture. Okay, so another issue here is memory bandwidth. With two memories, you're going to have less chance of a bandwidth problem because the different devices are going to be pulling from different memories, and it's quite easy to pull from the two different memories at the same time. Now that'd be pretty hard to pull to read from two different areas of the same memory at the same time. So that's another advantage of this thing is Harvard, technically speaking, would probably have less memory bandwidth issues. Recall that memory bandwidth is kind of the rate, most important word there, rate at which I can pass data to and from a memory. So once again, if I have two different devices needing to pass data to and from the memory, it's going to bring up memory bandwidth issues. Another issue here is you have two memories. Smaller memories are cheaper than one large memory, so it could possibly save you time. And lastly, for you CPEs out there who are going to go on further into computer architecture, you'll get into the issue of pipelining. And pipelining is the notion of essentially, for example, we have what our process is doing. If it does a fetch, then it does an execute, and it does a fetch and an execute. Well, there's nothing to stop it from doing the fetch of one instruction at the same time as executing another instruction. So effectively, and I could actually, roughly speaking, theoretically speaking, get one instruction executed per clock cycle. Now, essentially, once again, what that means is we did the hardware set up such that it's doing like a fetch and execute at the same time. We don't have the hardware set up to do that, but if we were doing that, two different memories is going to provide a better support of that than one memory. In fact, having one memory would be kind of hard. Okay, so I think that's it on that thing. The only thing I wanted to say on this one is the RISC-V has one memory, right? One memory. Okay, well, the memory is just really complicated. It's just like this magical memory that does other stuff. And so what we talked about are these architectures, the difference being like one memory versus two memory, but the technical differences has to do with the data paths. So if they have separate data paths for address and data, or program memory and data, that is technically the definition of it. So our RISC-V, it does have separate data paths for program and data, so that technically makes it a Harvard architecture, even though we have one memory. Okay, so that's arguable there, but it's easier to say, hey, look, RISC-V has one memory, let's call it a von Neumann. But I think in the technical definition of computer architecture, which is there's going to be a separate data path for the data memory and program memory, I think technically RISC-V is a Harvard architecture. Okay, so just throw that out there. So the other issue we run into with computer architecture that you just absolutely have to take away from the course is CISC versus RISC. So RISC is reduced instruction set computer. Look, we've been using that term for many weeks now, and now you know what it is. Okay, and there's also a CISC. CISC is complex instruction set computer. Now, you gotta be careful with these names because Reduced instruction set makes it seem like if there's few instructions, it's automatically a RISC, which is absolutely not the case. That whether it's a RISC or CISC has to do with other issues, and these are the other issues. So RISC architecture generally has very simple instructions, and relatively speaking, our RISC-V, the instructions are very simple. We don't have anything like square root or sine and cosine or division or stuff like that, or even multiplication. Our instructions are very simple, and because they're simple, hey, look, they mostly operate in the same number of clock cycles. Now, I know we have a load instruction that operates in 3 clock cycles, and then all the other instructions operate in 2 clock cycles, but that's pretty close anyway. So that's what we have in other architectures is like, some instructions take 1 clock cycle, and some instructions take 8 and 10 clock cycles. It's architecture dependent and instruction set dependent. So we also, RISC processors also have large register files. Now, a large register file is really advantageous because the working with registers is fast. Now, it's fast because all the fun operations are ALU based. They work through registers and not through memory. So that means if I have to do some type of mathematical operation on a value in memory, I first have to load it into a register, do the operation, then possibly store it back out to memory. Okay, it's a little bit slower, so these RISC architectures generally have larger register files. I've seen even like high-end processors typically have really tiny register files, and they work by swapping data in and out of memory. Lots of times we don't need to do that because we can store a lot of that data in registers. You saw in a previous example that the registers are fast, yes, but they're not generic. The register used in any instruction is fixed at assemble time, whereas when you're accessing memory, you can access memory through an address. Address could be represented by a register, which is essentially a variable, and you can change essentially the values in those registers to act as a variable. So there's a lot to it, okay? That's what I'm trying to get at here. And lastly here, generally speaking, what you have in a RISC architecture is a fast clock cycle because the instructions are simple. So you have a fast clock cycle. Instructions operate simply as compared to a CISC, where usually the clock cycle is slower, but the instructions generally get more done per instruction. So generally speaking, if you write a program in a RISC architecture, you can have a lot more instructions, but the instructions are going to execute faster. If you write it on a CISC, it's going to have less instructions, but it's going to take longer to execute those instructions. So now the issue here is reduced instruction set. Once again, it has nothing to do with the number of instructions in the set. It's a common problem that everyone asks, and so don't fall into that. Now, the number of instructions in the instruction set has nothing to do with it being a RISC or a CISC. Okay, so anyway, these are the overall differences here. RISC programs have fewer instructions, operate fast. RISC programs have more instructions, require more instruction to do the same job, but it operates faster than a CISC processor, which takes fewer instructions, but once again the clock cycle is going to be lower. The clock speed. So there's always some definitions you have to take away from this course, and one of them is data path, and the other one central processing unit. Now these are instructions that once again, look, I should know these, but I forget what they are, partially because people define them a little bit differently. But other than that, I just can't remember them. And so when I can't remember something, I don't require anyone else to know it either. What I can tell you is I do understand how all the hardware works, and that's what I want you to understand. But common terms here are data path. Okay, data path, that means something. Number one, generically speaking, it means the path that the data is taken, but it is an architecture sort of term, and it's defined by some stuff. And here's the stuff for the data path. When they say data path in the context of architecture, generally means ALU register file and the various selection logic associated with ALU and register file. Okay, generally speaking, data path. Okay, lots, like I said, you see other people have different definitions of it. One working definition I've actually kind of uses, it's pretty much everything that's not part of the control unit. So it's the entire process, entire block, whatever block time. I'm trying not to say CPU. It's the entire schematic, not including the control unit. And so the control unit, so the central processing unit, is the entire schematic. Now the difference is that sometimes these higher end or even other standard microcontrollers have external peripherals in them, which is just an external piece of hardware such as a counter, timer counter, A to D, D to A. What else? They have comparators. They have a lot of different things on them that are not part of the computer, say, but they're just helpful external hardware. So I would say the CPU is everything except possibly external peripherals. Okay, and once again, you should know these things. Once again, I kind of trip up on them, so don't freak out over them. This one's actually pretty easy to memorize. Data path, I kind of like this definition as where it's everything except the control units. And that's it.